Welcome to Probability, the Next Level, starring your very own Miss Phillips. Now this little tutorial is to help you figure out some of the major concepts in probability that could be a little trickier to get sometimes. First of all, let's look at the differences between experimental and theoretical probability, as well as the differences between combinations and permutations. Let's go ahead and dive right into experimental probability. Experimental probability is just how it sounds. It's the probability of something happening based off of an experiment. Experimental probability is where you say, this is what I expect to happen because this is what happened before. To set up a situation for us, let's take this number cube. We know we've got 6 different numbers to choose from. It's a regular fair die, so it's labeled 1 through 6. Now, if we're going to run trials where we roll this die numerous times and record our results, we're going to need a table to help us out. So go ahead, set up a table on your paper. We could label one column the trial number to show which roll we're on, and the other one, just number, so we can record what we got. Alright, so for trials, it might be best to go ahead and do, 20 of them, whatnot. To save time, this is a tutorial and all, let's just go ahead and just pretend. So we roll it once, we got a 1. Roll it again, 5. Roll it again, 6. And so on and so forth. Now what we're going to do is take this data and pick one thing at a time that we're looking for. Now the formula for experimental probability is the number of times it happened, and by it we mean whatever you're looking for. It was just a whole lot shorter to write. Okay. Over, and when I say over, remember that's a giant fraction bar. Over the total number of trials. Now, if we're trying to figure out the experimental probability of rolling 2s, we're going to say, well, how many times did 2s show up? We look through our data, we circle all of the ones that were 2s. And we say, okay, they showed up twice out of 20 total rolls. Well, then our probability, after we reduced it like we're supposed to, would be 1/10. So we would expect that out of every 10 rolls of our number cube, we would get 1, 2. Now obviously it's experimental probability, so it's going to be different every time you run the experiment. Maybe it'll be different the more times you roll. That's why experimental probability isn't the actual probability behind something. Experimental probability just gives you an idea of what you would expect based off of what would happen before. Now, actual probability, that's where we get into theoretical probability. Alright, so theoretical probability, your very first job is to take whatever you're looking at. So let's go back to our number cube. And to come up with the sample space for that particular situation. So let's say our goal here is to roll this number cube. Well, the sample space is whatever the possible outcomes are. And on a number cube, the possible outcomes are rolling a 1, 2, 3, 4, 5, or a 6. Now once you have your sample space, you can go ahead and use your ratio for theoretical probability. So your ratio, your formula you're going to use, is the number of desired outcomes, so that's what you're looking for, over, giant fraction bar again, the total number of outcomes. Now, using our probability notation that we're used to, if we were going to look at the basics and say, what's the probability of rolling a 3? Well, we'd say, okay, well, how many of the numbers in our sample space are the number 3? Oh, just one of them. So the number of desired outcomes, well, just one of them is a 3. So you'd put 1 over, now the total number of outcomes is 6, because there are 6 possible choices. So the probability of rolling a 3 is 1/6. Now, theoretical probability, you can also extend it and say, okay, well, what's the probability of rolling a 3 or a 4? Well, you look through your sample space and say, well, 2 numbers satisfy those qualifications, the 3 and the 4. So the number of desired outcomes would be 2, and the total number of outcomes would still be 6, because 6 things could happen. Now, do remember that in probability we always reduce our fractions. So 2 over 6, 2 goes into 2 once, 2 goes into 6 3 times. So the probability of rolling a 3 or a 4 is 1/3. So theoretical probability is really what you know should, and I say should, because that's the equal likeliness. Each of the faces of this number cube are equally likely. So 1/3 chance of getting a 3 or 4, a 1/6 of a chance of rolling a 3. That's theoretical probability. It's the actual probability behind something happening. Okay, so just to recap, experimental probability is based off of an experiment, where theoretical is not. Theoretical probability is what should happen based off of the actual die or whatever situation you're using. Okay, next up, combinations versus permutations. There's a big difference there, and it's an easy one to remember. The difference is that in one of these, order matters. You ready to find out which one? Permutations. Permutations are different from combinations because the order in which things are placed matters. So for instance, you're in line at school. You definitely care where in line you are. That's a permutation. Because there's lots of different ways you could take you and all of your classmates and line you up. You could be in front of Susie, or she could be behind you. She could be 3 people back, and you could be in the very front. Combinations is just saying, hey, I need you 30 kids to come into this room for, I don't know, science class, I guess it is. That's a combination. That's just picking 30 kids. That's just grouping things. Permutations is saying, okay, line up in a certain order. Come sit in a certain spot. Because every different mutation is just different. Here's how I remember. Permutation has the word mutate in it. And mutate is like taking, let's say this really cool bear and mutating him. We're going to say, okay, bear, we're going to move your eyeball to your chin. Ta-da! We just mutated our bear. We changed the order of his face. So for permutation, order matters. All right, so let's move right in to the differences. Because obviously, if there's a difference between what they represent, there's going to be a difference in how you calculate them. Let's go ahead and start with the first one on our list, combinations. Combinations is where you just choose a group of things. So let's say that you and your friends, let's say James, Sarah, Ricardo, Kelly, and Mira are hanging out. And you're enjoying yourself with your friends, and then your mom says, hey, you, you want to go to the movies? Pick a couple friends. They can come with us. So, of course, you battle with your parents. You say, well, how many friends is that? What's a couple? And, of course, it always ends up being, a couple's 2, kid. So you get to pick 2 friends out of the 5 you have around to come with you. Well, this is a combination because you don't really care how you say, okay, Sarah, you're first. You're going to come with me first in the car. No. Order doesn't matter for this. You're just going to say, hey, 2 of you, you're coming with me. So there's lots of different possibilities. Now, we could make a list. We can absolutely make an organized list of this data. So let's see. We'd have, let's shorten their names. That'll make it easier on us. Abbreviate. We could have James and Sarah, or James and Ricardo, James and Kelly, or James and Mira. Now, we already used James and Sarah. So putting Sarah, James, that's still the same 2 friends. So that would be a different order, which for combinations doesn't matter. So we'll start with Sarah, Ricardo. Then Sarah, Kelly, Sarah, Mira. For Ricardo, we have left Kelly and Mira, and then for Kelly, just Mira. So if you add those up, your sample space here, we have 4 plus 3 plus 2 plus 1, for a total of 10 possible combinations. Now, if your friends, I don't know, Sarah and Kelly were like, hey, what's our probability of being picked together? You'd say, well, that's 1 option out of the 10 total. So you could easily turn this into a probability. Now, sometimes you're going to have a really big group of people or a lot of spots to fill or something where listing them, not convenient. For instance, your mom says, hey, there's 130 kids on your team at school. Let's bring 3 of them. Well, that's a lot of possible combinations. You wouldn't want to list them out. So, we have a special formula for combinations. Here is what it looks like. There's a little N, big C, little r. I like to read it in, choose R. The C stands for combinations. That's an easy one to remember. The N stands for the total number of options. And the R stands for how many you're picking. Okay, so let's just make sure this works with what we already know is correct. So, for our example, our N was how many options we had. Well, we had 5 of our friends to choose from. And we got to pick 2 of them to come with us. So R equals 2. Now let's save that to plug in when we know what the formula is. So here you go. You ready? The formula for calculating how many possible combinations there are is NCR equals N factorial over r factorial times n minus r factorial. Now do remember we covered factorials in class. Feel free to look it up online if you don't remember. You also have a textbook that would be helpful too. Okay, so plug in what we have. We knew our n was 5. So wherever you see an n, you're going to put the number 5. 5, choose 2, because that's our r. Okay, so here we go. 5 factorial over 2 factorial times 5 minus 2 factorial. Order of operations. We're ready to go ahead and say, that equals 5 times 4 times 3 factorial. And I'm going to pause there because in the denominator we have 2 factorial times 3 factorial. Well, the 3 factorial in the numerator cancels out with the 3 factorial in the denominator. So now when we're ready to simplify that, 2 factorial is just 2 times 1. And 2 goes into 4 twice. So in the denominator, all I have is a 1. And the numerator is 5 times 2, which is 10. Well, would you know it? It's exactly what we got before. So this formula can be used to do what we did with the list. Those are combinations. Okay, now that you have the formula, you know what n stands for, you know what r stands for, and we already proved that it works, let's go ahead and move on to permutations. Okay, so we know that for permutations, order matters. There we are. Now let's say you get to the movie theater. You picked a couple friends to go with you. It ended up being Kelly and Mira. So it's you, Kelly, and Mira. And you get to the movie theater and you find out that they're doing a special promotion. And everybody in line who lines up early for the movie gets a special edition poster. And every poster is different. Now obviously the position in which you hold in line matters because every spot gets a different poster. So now you guys are just hanging out waiting and decide, well, how many different possible permutations are there for us? Like, how many different ways could we have gotten these posters? So, to do this, you could still make a list. That would absolutely work. And here's what a list would look like. You'd say, okay, it could be you, and let's go ahead and abbreviate again. You, Kelly, Mira. It could be you, Mira, Kelly. Or what if Kelly was first, and then you, and then Mira? Or Kelly, Mira, and you. Or Mira could be first, with you, and then Kelly. Or Mira, and then Kelly, and then you. These are the possible permutations for this group of people. So this, let's go ahead and write it in there, would be the first spot in line, second spot, third spot. And order matters because you know those posters are going to be different. Okay, so now we know we can count 1, 2, 3, 4, 5, 6 total permutations. Guess what? If you had brought 20 of your closest friends, you could do the same thing. You could figure out exactly which order or how many possible permutations there were, but it would take a whole lot more work because that's a lot more options. We've got a formula for you. Here it is. It looks very similar to the combinations formula, but it has its differences. Here we go. In capital P, little r. Within that, the N still stands for the total number of options, but the R is basically the number of spots you have to fill. So, in this particular example that we've already talked about, we took you, Kelly, and Mira to the movies. So we had 3 people lining up and 3 spots. So our N is 3, and our R is also 3 because we have 3 spots to fill. Well, I know right now you're asking yourself, well, wouldn't they always be the same then for permutations? Not true. Not true. Because sometimes maybe you showed up with 20 of your friends and only 3 people could get in line because they were at their limit. Well, then you'd have 20 people to choose from, 20 options, but only 3 spots to fill. Okay, so here comes the big bad formula. N PR equals N factorial over N minus R factorial. Just a subtle difference. On combinations, we had an extra R factorial in the denominator. We do not have that in the permutations formula. This is what takes out the repeats. This right here is what makes it so that order doesn't matter for combinations, and not having it in the permutations formula says that the order does matter. Because obviously we have the same 3 people over and over again up here. Okay, so taking that formula, let's fill in our data for our example. We know that N is 3, R is 3, so plug it in. Okay. When you've done that, go ahead, order of operations. We know that 3 factorial is 3 times 2 times 1. In the denominator, 3 minus 3 is 0. 0 factorial, and make sure to make a note of this, 0 factorial always equals 1. That's a big deal. So when we simplify this, we'll have 3 times 2 times 1 over 1. Do our multiplying. 3 times 2 is 6, times 1 divided by 1 equals just 6. 6 total permutations, just like we thought. So clearly, that matches up with what we got when we listed them out. So if you have fewer number, feel free to make a list. It'll help you out. If you have a lot of options to choose from and you're trying to figure out permutations, I suggest using the permutations formula. All right, so let's wrap this up. We had the differences between experimental and theoretical probability. We also found the differences between combinations and permutations. Go forth and practice on your own, my dear ones. I know you can handle this. You guys rock.